This is going to be the first of 3 lectures on using matrices to represent systems of equations and talking about the steps that we use to solve those systems using the matrix representation. To begin, let's talk about what a matrix is. A matrix is just a rectangular array of numbers. So you can see we've got a bunch of entries inside of these large square brackets. The first entry is A11, and the 1 indicates that we're in the first row and the first column. Next to that you see A12, which is in the first row, second column, and so on until we get to the last column, which I've called column N. So we have N columns. Underneath A11 you see A21, which indicates that we're in the second row, first column. And next to that A22, second row, second column, and so on. All the way down to the bottom, which I've denoted the mth row. So mth row, first column, mth row, second column, all the way to the mth row, nth column. So this example has m rows and n columns, and so we call it an m by n matrix. This is read m by n. One more bit of notation before we move on to a matrix representation of a system. We're going to be working primarily on the rows of each matrix, and so I want you to get used to this notation. R sub 1 means row 1, so the first line of our matrix would be R1. R2 means row 2, and so on all the way down to Rm, which would mean row m. We're going to use this notation when we're solving systems using matrices, so I just wanted to introduce that now. How do we represent a system of equations with a matrix? Well, here's an example. We've got the system x plus 3y equals 10 and negative 2x plus 5y equals negative 9. When we solve a system of equations using the elimination method, if we keep all of the variables in line, then all we're really tracking are the coefficients. We don't have to constantly recopy the variables over and over. So what we're going to do is make a rectangular array of the coefficients and the numbers on the opposite side of the equal sign. So for example, I can represent the first equation by copying the coefficient of the first variable, x, which is 1, then copying the coefficient of the second variable, which is 3, and then copying the number on the other side. And to kind of indicate where the equal sign is in our equation, we often put a line segment like this, dividing the coefficients of the variables from that number on the other side. A matrix written like this is called an augmented matrix. I'm going to do the same thing for the second equation. I want to make sure that all of my variables are lined up the same. Like I've kind of created an x column here. So since I put the coefficient of x first in the first row, I want to put the coefficient of x first in the second row. Of course, that's how it's already organized, so you were probably going to do that anyway. Negative 2 first, 5 second, and then a negative 9 on the other side. And then we'll close up the matrix like this. This matrix represents this system of equations. All we've really done is taken out the unnecessary copying of the variable. We've kind of indicated that the first column represents the coefficients on x, the second column represents the coefficient on y, and the right side is some constant term. We can solve this system using the matrix representation using the exact same steps we would use if we were solving the system by the elimination method. So for our first example, we're going to solve this exact same system, and first I'm going to do it by the elimination method, and then I'm going to do it with the matrix representation to show you how that would look. So if I were solving this system using the elimination method, I would multiply the first equation by 2, and I would get 2x plus 6y equals 20, and negative 2x plus 5y equals negative 9, and then we would add those equations together to get a new equation, which would be 11y equals 11, and then we would solve for y equals 1, and then we could back substitute and solve for x, and we get x plus 3 times 1 equals 10, so x plus 3 equals 10, so x equals 7, and our solution is 7, 1. Let me use the matrix representation that we came up with last time to do the exact same thing. I'm going to start by writing out the matrix representation of this system, which is 1, 3, 10, negative 2, 5, negative 9. This matrix is 2 by 3 because it has 2 rows and 3 columns. I'm going to divide off the coefficients of the variables from the numbers on the other side with this line segment. Again, we call this an augmented matrix. The first thing we did when we did this by the elimination method is we multiplied the first equation by 2 and then we added the 2 equations together. I want to do the exact same thing here. I'm going to take 2 times the first row and I'm going to add that to the second row. And when I do that, I'm going to replace one of the rows. I'm going to replace row 2, so I'm going to use this arrow to say, now put that into row 2. So I take 2 times the first row, that's 2 times 1, and I add that to the second row. 2 times 1 plus negative 2 is 0. I'm going to replace the entry in the second row with that. I'm going to do the same thing to the next entry. 2 times the entry in the first row, so 2 times 3 is 6, plus the entry in the second row. 6 plus 5 is 11. Put in that line dividing. 2 times the entry in the first row would be 2 times 10 is 20, plus the entry in the second row. 20 plus negative 9 is 11. If we translate our new row, it says 0x plus 11y equals 11, which is exactly what we have here. It's the exact same step, but we're not writing out all of the x's and y's each time. We're also not writing the equal sign that's kind of represented by this divider here. Now we want to keep the array 2 by 3, so I'm going to keep the first row exactly the same. We're not changing the first row. If I want to solve this equation for y, because remember this is the y column, then I need to change this coefficient to a 1. Over here we divided both sides by 11. In the matrix format, we typically describe the step as a multiplication step. I'm going to take 1/11 of row 2, and I'm going to replace row 2 with that. So 1/11 of 0 is 0, 1/11 of 11 is 1, and 1/11 of 11 is 1. And now this basically says 0x plus 1y equals 1, or y equals 1. I'm again not changing the first row. And in our lectures, when we get the value of one of the variables, we're going to dump out of the matrix representation and use back substitution to get the rest. So this tells me that y equals 1, and now I can go back to the first row and translate it. Now we never changed it, so it still means the same thing. It says x plus 3y equals 10. And now I can back substitute x plus 3 times 1 equals 10, and you can see we're in the exact same spot. We're doing the exact same work. X plus 3 equals 10, x equals 7, and we get the solution 7, 1. We actually could keep altering the matrix until we got down to what we call reduced row echelon form, where we have all 1s down the diagonals and 0 everywhere else. When we're doing this by hand, we're just going to do enough work to find out the value of one of the variables, and then after that we're going to dump out of the matrix representation and do the back substitution by using the equations. I hope you can see the parallels between the two techniques. I mean, it's pretty much the same thing. Now, a common argument is, why would we even mess with this matrix representation when we already know how to do this by hand using the addition method, the elimination method that we were talking about before? Well, as the number of variables and the number of equations increases, the matrix representation becomes more and more useful. So we're going to do this for more variables and more equations. Another benefit is that it's very easy to represent these matrices with technology, and eventually we're going to learn how to use the calculator to do this stuff for us in the really complicated scenarios. Our next system has 3 equations and 3 unknowns. Solve the system x plus y plus z equals 6, negative x minus 3y plus 2z equals negative 1, and negative 5x plus 2y plus z equals 2. We're going to solve this by coming up with a matrix representation. If you'd like to try solving this by hand using the addition method, the elimination method, I encourage you to try it, but it's the exact same steps, and you're going to wind up writing all those x's, y's, and z's over and over again unnecessarily. Because we have 3 equations, we're going to need 3 rows. And because we have 3 variables and then a constant on the other side, we're going to need 4 columns, and we're going to separate off that 4th column with this line segment. We're going to create a column of x coefficients, a column of y coefficients, and a column of z coefficients. Copying the coefficients from left to right in the first equation, we get 1x, 1y, and 1z is equal to 6. We get negative 1x minus 3y plus 2z is equal to negative 1. And we get negative 5x plus 2y plus 1z is equal to 2. What we'd like to do is get one of these rows to have 2 zeros and a 1 in it on the left side of that line segment. If we can get 2 zeros and a 1, then we'll know the value of that variable. And the standard strategy is to try to get a column with 2 zeros first. So you can see we don't have any zeros here. We want to create a couple of zeros. And I'm telling you now, your best friends in this technique are 1s and -1 because it's easy to create zeros with a 1 or a -1. So for example, this 1 right here, I can use that to create a 0 directly underneath it by just adding row 1 to row 2. I'm going to add row 1 to row 2. Now when I do that, I could replace either row 1 or row 2. I'm kind of looking at it like I'm using row 1 to change row 2, so I'm going to put that into row 2. So I'm not altering row 1. And in row 2, I'm going to put the sum of row 1 and row 2. So 1 plus -1 is 0, and 1 plus -3 is -2, and 1 plus 2 is 3, and 6 plus -1 is 5. That new equation says -2y plus 3z equals 5, which is what we would get from just adding the first two equations together. It's the same thing, we're just using a matrix representation. We're not unnecessarily copying down the variables over and over again. Now my next goal is to create another 0 underneath that 1. If I can do that, then I will have eliminated the x's in the last two equations, and the bottom two equations will have two variables, and then we can eliminate one more of those, and we'll be able to find the value of either y or z. So how am I going to turn this into a 0? Well, I can take the 1 in the first row, multiply it by 5, and then add it to the third row. And that's exactly what you'd do if you were working with the equations. If I told you I wanted you to eliminate the x's, you'd take 5 times the first equation and add it to the third equation. We're going to take 5 times the first row and add it to the third row. And we're going to use that to replace the third row. So 5 times 1 is 5, plus -5 is 0. 5 times 1 is 5, plus 2 is 7. 5 times 1 is 5, plus 1 is 6. 5 times 6 is 30, plus 2 is 32. And this row translates to 7y plus 6z equals 32. Now, I'd like to make one more 0 in those bottom two rows. Can you see an easy way to do that? If we take this 3 and multiply it by -2, that would give us -6. And when we add that to the 6, that would give us 0. So that's going to be my step. I'm not going to do anything to the first row. I'm not going to do anything to the second row. So we're going to take -2 times row 2. We're going to add that to row 3, and we're going to let that replace row 3. Now here's the beautiful thing about creating these zeros. Those will not change. When I take -2 times 0 and add it to 0, I still get 0. -2 times -2 is +4, plus 7 is 11. -2 times 3 is -6 plus 6 is 0, and we've eliminated the z from the last equation, from the last row. Now this is just in terms of y. -2 times 5 is -10, -10 plus 32 is 22. This last row translates to 11y equals 22, and so that means that y equals 2. The way we would show that in the matrix representation is to multiply the last row by 1/11. I take 1/11 of row 3 and replace row 3 with that. I get 0, 1, 0, 2. I'm not changing the first row. I'm not changing the second row. So now we know that y is equal to 2. We could continue eliminating entries in the matrix until we found x, y, and z in the matrix form. But in my lecture, as soon as we get one of the variables, we're going to go back to translating the equations and finding the values of the other variables by using the equation format, back substituting. So I'm going to translate row 2 into an equation. Row 2 says -2y plus 3z equals 5. How do I know that? Well, remember, we put all of the x coefficients in the first column, we put all of the y coefficients in the second column, and all of the z coefficients in the third column. In row 2, the x coefficient is 0, so there are no x's. We just have -2y plus 3z, and then this line segment is where the equal sign goes, equals 5. Well, we just figured out that y is equal to 2, so -2 times 2 plus 3 times z is equal to 5. So -4 plus 3z equals 5. So 3z equals 9, so z is equal to 3. Now I can translate row 1, which doesn't really need translating because we never altered it. It says x plus y plus z equals 6. And we know y is 2 and z is 3. So x plus 2 plus 3 is equal to 6, which means that x equals 1. So x is 1, y is 2, and z is 3. It's common to write that solution as an ordered triple. Our final answer is 1, 2, 3, with x going first, y going second, and z going last. Now that obviously works in the first equation. 1 plus 2 plus 3 is 6. Does it really work in the second equation? Negative 1 minus 6 plus 6 is equal to negative 1. Yeah, that works. Does it work in the last equation? Negative 5 plus 4 plus 3 would be negative 5 plus 4 is negative 1. Negative 1 plus 3 really is 2. Yeah, it works. This matrix representation is just a shorthand way to keep track of the coefficients and the numbers on the other side of the equation. It's very similar to what we did with synthetic division, actually. Let's keep trying examples. Here we have a new system. 2x minus 3y plus z equals 26. 4x plus 5y plus z equals 30. And negative x plus 4y minus z equals negative 18. I'd like you to try to come up with the matrix representation of this system. You're going to need 3 rows and you're going to need 4 columns. So come up with a 3 by 4 augmented matrix that represents this system. Pause the video and see if you can do that. The variables are already organized in the column, so I can just copy down the coefficient on the left side and then copy down the number on the right side. 2, negative 3, 1, 26 for the first equation. 4, 5, 1, 30 for the second equation. Negative 1, 4, negative 1, negative 18 for the third equation. There's our matrix representation. I'm going to copy this on another slide so we have a bit more room. Okay, I have our matrix copied down on the next slide. I want to create some zeros, and there are a couple of good ways to do that. I could use the negative 1 down here to turn these into zeros without much difficulty. A couple of multiplication steps and I could do that. But my eyes are drawn to this last column, which has all 1s and negative 1s. I can make some zeros here very easily just by adding some rows together. I'm going to add row 3 to row 2, and I'm going to add row 3 to row 1 to make some zeros. So I'm going to revolve everything around row 3, and because of that, I'm going to replace rows 1 and 2. So the first thing I would do is add row 3 to row 1 and let that replace row 1. Then I would add row 3 to row 2 and let that replace row 2. I'm not going to alter row 3 at all. So negative 1 plus 2 is 1. 4 plus negative 3 is 1. Negative 1 plus 1 is 0, which is why we did that. That eliminates the z from the first equation. And negative 18 plus 26 is 8. I'm going to do the same thing with row 3 and row 2. Negative 1 plus 4 is 3. 4 plus 5 is 9. Negative 1 plus 1 is 0, and we've eliminated the z from the second equation. And negative 18 plus 30 is 12. We're not changing row 3. Now I'm going to focus on just the first 2 equations and see if I can make one more 0. If I can eliminate any of these 4 coefficients, if I can make any of these a 0, then I can solve for the variable that's left over in that row. I don't want to use the third row to do that. If I add the third row to either the first row or the second row, that's going to undo the zeros that I just did. So I'm looking for a way that I can use row 1 to eliminate something in row 2 or vice versa. And we have a couple of good options because we've got a couple of 1s sitting up here. We love 1s and negative 1s. If we multiply row 1 by negative 3 and add it to row 2, that's going to turn this into a 0. So I'm going to leave row 1 alone, but I'm going to replace row 2 with negative 3 times row 1 plus row 2. So negative 3 times 1 is negative 3, plus 3 is 0, and I've eliminated the x's in the second column. Negative 3 times 1 is negative 3, plus 9 is 6. This is why we wanted to use the first and second rows. We don't change the 0. Negative 3 times 0 plus 0 is still 0. Negative 3 times 8 is negative 24, plus 12 is negative 12. We're not altering the third row. And now this second row says 6y equals negative 12. To solve that for y, I'm going to take 1/6 of row 2 and put that into row 2. So row 1 still says 1x plus 1y plus 0z's equals 8. The second row now says 0x's plus 1y plus 0z's equals negative 2. And the last row I'm not changing. At this point we know y equals negative 2. Now I need to back substitute. Which row are we going to translate for our back substitution step? We want to use the first row because it only has two variables. If I try to back substitute in here, when I replace the y, I'll still have an x and a z, and I won't be able to solve for one of them. But in row 1, we can solve for x. We know that x plus y is supposed to be equal to 8. Well, that means that x minus 2 is equal to 8, so x is equal to 10. Now I'm going to use row 3 to solve for z. I know that the opposite of x plus 4y minus z is equal to negative 18. So negative 10 plus 4 times negative 2 minus z is equal to negative 18. So that's negative 18 minus z equals negative 18, so z must be equal to 0. And our solution is the ordered triple 10, negative 2, 0. Let's go back to the original system. We're claiming the solution is 10, negative 2, 0. We know that works in the bottom equation. Does it work in the first equation? 2 times 10 is 30. Negative 3 times negative 2 is 6. 20 plus 6 plus 0 is 26. Yeah, that works. What about in the second equation? 4 times 10 is 40. 5 times negative 2 is negative 10. 40 plus negative 10 plus 0 is equal to 30. Yeah, this works. Let's try another. This system says 3x plus 2y plus 2z equals 0. Negative 4x minus 2y plus 7z equals 13. And 5x minus 3y minus 6z equals 14. I want you to translate that into a matrix for me, please. Did you get this? Okay, from here, we need to start creating some zeros. We want to create a column with 2 zeros in it. I want you to find a number that's going to be easy to create zeros with. It's this 1, in my opinion, that's going to be the easiest to do. Everywhere else we'd have to use fractions, but this 1 is going to create zeros pretty easily underneath it. See if you can do that. I want you to create zeros in the second column in row 2 and row 3. I'm not changing the first row. 3, 1, 2, 0. To get a 0 in the second row, I can take 2 times row 1 and add that to row 2. 2 times 3 is 6, plus negative 4 is 2. 2 times 1 is 2, plus negative 2 is 0, that's why we did that. 2 times 2 is 4, 4 plus 7 is 11. 2 times 0 is 0, plus 13 is still 13. How are we going to make this a 0? Well, we'll multiply row 1 by 3. 3 times row 1 plus row 2. Put that into row 2. 3 times 3 is 9, plus 5 is 14. 3 times 1 is 3, plus negative 3 is 0. That was the point. 3 times 2 is 6, plus negative 6 is 0. We got a bonus 0 for free here. And 3 times 0 plus 14 is 14. Here we're not going to have to do another elimination. This row already tells us the value of x. To get it in the matrix format, I'm going to take 1/14 of row 3 and put that into row 3. I'm not changing row 1, and I'm not changing row 2, but row 3 becomes 1, 0, 0, 1, and so we know that x equals 1. Now we can back substitute, and I can either back substitute by translating the first row or the second row. Which one do we want to use? Well, we want to use the second row because it only has two variables. So row 2 says 2x plus 11z equals 13. Well, I know x is equal to 1, so 2 times 1 plus 11 times z equals 13 means that 2 plus 11z equals 13. So 11z equals 11, so z is also equal to 1. Now I'm going to translate row 1. 3x plus y plus 2z equals 0, which is the original first equation. We haven't changed it at all. I know the value of x is 1. I don't know y. I know the value of z is 1. And so I get 3 plus y plus 2 equals 0. So y plus 5 equals 0. So y equals negative 5. And our solution is 1, negative 5, 1. We know that works in the first equation. I'll leave it to you to check to make sure it works in the last two. One more example. And here I'm going to help you with the matrix setup, and then I want you to finish it off. This one's a little bit different because you'll notice that variables are missing in a couple of the equations. The first equation says x minus 3y equals 10. The second equation says 2x plus z equals 0. So we're missing variables in each of those two. The last equation is more what we're used to, x plus y plus z equals negative 4. To translate the first row, I'm going to use 1x, negative 3y, and then since there are no z's, I'm going to use a 0. It's like that's already been eliminated for us. Then a 10 on the other side. Here, be careful, it's 2 x's, it's no y's, and 1 z. Make sure you keep the coefficients for y and z straight, and then 0 on the other side. And the last row is 1, 1, 1, negative 4. I'd like to create a column with 2 zeros. And just so we all get the same step, I'd like you to turn this into a 0. For those of you looking ahead, I know that's going to change this from a 0, but we're not going to be able to avoid that. We're going to have to change one of these zeros as we eliminate. So I'd like you to turn this entry into a 0 by using the third row. I'm going to take 3 times row 3 and add that to row 1 and put that into row 1. So 3 times 1 plus 1 is 4. 3 times 1 is 3 plus negative 3 is 0. 3 times 1 is 3 plus 0 is 3. 3 times negative 4 is negative 12 plus 10 is negative 2. I'm not altering the second row. I'm not altering the third row. Now I know that got rid of a 0, but what's more important is that we've now eliminated the variable from 2 of the rows, from 2 of the equations. So now we can focus on the top and eliminate one of the variables. You could go after the x's or you could go after the z's. It doesn't really matter to me which way you do it, but because we've focused on these ones, I'd like you to go after the z's here. You would do that by taking negative 3 times row 2 and adding it to row 1. If your idea was to take negative 2 times row 2 and add it to row 1 to get rid of the x's, that's also correct. I only asked you to go after the z's because I wanted you to have the same steps as me. So negative 3 times 2 is negative 6, and negative 6 plus 4 is negative 2. Anything times 0 plus 0 is still 0. Negative 3 times 1 is negative 3 plus 3 is 0. Now we can solve for x. Negative 3 times 0 is 0 plus negative 2 is negative 2. 2, 0, 1, 0, 1, 1, 1, negative 4. And now we can multiply row 1 by negative 1 half. Negative 1 half times row 1, replacing row 1, gives us 1, 0, 0, 1. I'm not doing anything to the second row. I'm not doing anything to the third row. And now I know that x is equal to 1. Back substitute to find y and z. To find z, you're going to start with row 2. We know that 2 times x plus z is equal to 0. So 2 times 1 plus z is equal to 0. So 2 plus z equals 0, so z equals negative 2. Now I can use row 3 to finish this off. I know that x plus y plus z is equal to negative 4. So 1 plus y plus negative 2 equals negative 4. So y minus 1 equals negative 4. So y equals negative 3. So our solution is 1 comma negative 3 comma negative 2. Make sure you put it in order. X first, then y, then z. Again, I'll leave it to you to check that those work in the first 2 equations. It certainly works in the last equation because that's how we generated the value of y. You're definitely going to want to practice some of these problems. It's not enough to watch somebody else do them, not only because you're not thinking for yourself, but also you might have different ideas. Maybe you thought some of the steps I used weren't the best way to do it, and your brain really wanted to go another route. You need to follow those instincts. Don't do it the way I would do it. You have to practice with the matrices, no cheating, leaving it in equation form. Make sure you can do this in matrix form. But maybe you wanted to eliminate different variables than I did. Maybe you've learned this before and you learned to get all ones down the main diagonal. Do it that way, that's fine. Just make sure you get in some practice. We're not going to have any more examples of doing this by hand in our lectures because we're going to move on to doing this with the calculator. But I need to make sure you can do this by hand because some of you will be moving on to classes that use matrices and I want you to be comfortable with them. If you have any questions about my examples or any of the examples you're trying from a textbook, please reach out to me. You can see me in an office hour or we can do things by email.